Welcome to Control System classes. The topic for today's discussion is root locus from electrical engineering talk. Let us discuss example 1. The given open loop transfer function is g of s is equal to k into s plus 9 divided by s into s square plus 4s plus 11. It is asked to sketch the root locus and to find the stability of the system. K represents system gain, G of S represents open loop transfer function. So first step is to find the location of poles and zeros. It means equate the numerator polynomial to 0, denominator polynomial to 0, find the roots. So let us equate the denominator polynomial to 0. So S is equal to 0 is 1 root, S square plus 4S plus 11. On solving it gives a complex pole of value minus 2 plus or minus j 2.64. Let us equate the numerator polynomial to 0. So the 0 is at s is equal to minus 9. So totally we have 3 poles plus 1 0. So 0 at minus 9, pole is at 0, minus 2 plus j 2.64 minus 2 minus j 2.64. Let us mark the poles and zeros on the S-plane representation. X-axis is sigma, Y-axis is j omega, which is nothing but an S-plane. So the poles are marked with a cross. So 0. Here minus 2 plus or minus j 2.64. Then a 0 is marked at minus 9. Step number 2. Find the number of root locus branches. Here from the given system G of S, we understood that P is greater than Z and the number of poles is 3, number of zeros is 1, P is greater than Z. So the number of branches is equal to nothing but number of poles is equal to 3. Right? So how many branches will approach infinity? We know that P minus Z branch will approach infinity. P minus Z is 3 minus 1. It means 2 branches will approach infinity. Remaining 1 branch, Z is equal to 1, will end at open loop 0. So we need to calculate 2 asymptotes as 2 branches are going to approach infinity. From this point, we are concluding it. The step number 3 is to determine the possibility of existence of root locus. We need to consider only the real axis, not the complex poles for step number 3. So on the real axis, we have 1 pole and 1 zeros. It means assume a test point here to the left of first pole. So let us assume a test point here. So I'm going to assume a test point A here. So to the right of my test point, I have total number of real poles and real zeros is 1. 1 is an odd number. So between 0 and minus 9, there is a possibility of existence of root locus when k is varied between 0 to infinity. Similarly, assume a test point B to the left of minus 9. So now to the right of B, you count the number of real poles and real zeros. So real pole and real zero is equal to 2. So this is an even number. So there is no possibility of existence of root locus between the point minus 9 and minus infinity. So the root locus existence is only between 0 and minus 9. How many branches is approaching infinity? We got the information from the previous slide. That 2 branches will approach infinity and 1 branch will end at 0. So it is just sufficient to calculate 2 asymptotes, and meeting point of asymptotes on the real axis is nothing but centroid. So let us see the formula of asymptote and centroid. Asymptote is plus or minus 180 degree into 2q plus 1 divided by p minus z. P represents number of poles, z represents number of zeros, q represents the value between 0, 1 to p minus z minus 1. As we require 2 asymptotes, so it is sufficient to substitute q as 0 here. So when we substitute q as 0 here, I got the value as plus or minus 90 degree. Right? So meeting point of asymptotes on the real axis is called centroid. So let us calculate centroid. The formula for centroid is sum of poles minus sum of zeros divided by p minus z. From step number 1, substitute the information of poles, zeros, p minus z is 2, and we got the centroid value as plus 2.5. Let us mark all the value on the plot. So here the poles and zeros were mentioned, and between 0 and minus 9, there is a possibility of existence of root locus. So it is shown in dark line. So let us mark centroid. The centroid is at plus 2.5. Meeting point of asymptote on the real axis is a centroid. So it can come on positive side or negative side. No need to worry. What information you got, you just mark on the plot. So plus 2.5. Then the angle is plus or minus 90 degree. So take your protractor and keep your protractor center point on the centroid. Then you measure plus 90 degree. Plus 90 degree means you need to go with anti-clockwise, and if it is a minus 90 degree means you need to go with a clockwise. So plus 90 means you need to go with anti-clockwise. So mark plus 90 degree and minus 90 degree. So these are the guidelines how the branches may approach infinity in search of zeros. The next step is breakaway and break-in. So from the given information we got that we have two poles, that is one real pole, then one real zeros, and one pair of complex poles. Now from this information we can understood that this always the branches will start at pole and end at zero. So this pole have the probability to meet the zero and end there. Similarly, these two poles may approach infinity by following the angle of departure procedure, right? So, as no branches are going to break away, it means this pole, this zero is not interested to break away from this point and to approach infinity. They are not interested to break away from this point and to approach infinity. So, this is not possible. Is it right? So, from the given concepts, from the concepts we had discussed, this is not possible. So this point can be skipped here. Breakaway and break-in is not applicable for the given problem. Then angle of departure is possible here as we have a complex pole. As we don't have complex zeros, angle of arrival is not required. Only we need to solve angle of departure. So to solve angle of departure, first step is write the formulas. Then let us take the first complex pole as P2, join all the real poles and other complex poles and real zeros to the point P2. Right? So all the poles and zeros are joined. Either it is real or non-real, all has to be joined. Then keep the protractor here, that is on the pole 0. Then you measure the angle. Then note it as θ1. Similarly, keep the protractor here, protractor center point on the pole and measure the angle. Keep the protractor here and measure the angle θ1, θ2, θ3. Right? So measure the angle and write the angles here. And we know that if we are moving in the anti-clockwise direction, the angles are positive. So the angles are mentioned in positive, right? So angles are mentioned in positive as we are measuring the angles in anti-clockwise. So here I got the angle of departure as minus 16.4. For the next case, I got angle of departure as plus 16.4. So keep it as such, we'll discuss in the next step. Then the next is we are going to discuss about intersection points of root locus branches with an imaginary axis. There are two methods to solve this, by trial and error method or by Rouse-Thoburg's method. Here I have solved with trial and error method. So from the given transfer function g of s, first find the characteristic equation, that is 1 plus g of s h of s equated to 0. Then in this equation, substitute s as j omega. S is equal to j omega is substituted in this equation. We know that j square is minus 1. So j is went off here as j square is minus 1. If we have j cube, it will give minus j. So like that we frame this equation. Then separate the real component and imaginary component. Equate the real component to 0. When we equate the real component to 0, I got k as 8.8. Then substitute k as 8.8 in this equation and get omega. I got the value of omega as plus or minus 4.44. As k is positive, it means there is an intersection at plus or minus j 4.4. 4.4. If k is negative, there is no intersection. It means the two branches will follow angle of departure angle and then it will cut the point plus or minus 4.44 and it will approach infinity in search of zeros. Right? So let us draw the final plot. Now let us combine all the steps we had solved into a single plot, and we'll discuss about the stability of the system. We'll conclude about the stability of the system. So this is my imaginary axis. This line is my real axis. The scales are marked here. Root locus is a symmetrical graph. So all the scales are marked equally off on the above the imaginary axis as well as below the that is below the real axis, above and below the real axis, right? So here the pole is marked at 0. 0 is marked at -9. The complex poles are marked here, -2 plus or minus j 2.64, and it is named as P2 as well as P3, right? Asymptotes and centroids are marked. They are not the final plot. They are simply the guidelines, right? So here, one pole, we know that the branches will always start at a pole and it will end at 0. So from 0, the branch will start and it will travel and it will end at the open loop 0 -9. So this is my first branch. Then what is my second branch? The second branch, to determine the second branch, we need to mark the angle of departure. So angle of departure at P2 is -16.4. So take your protractor, keep your protractor center point on P2, then keep the protractor downwards as we need to mark -16.4. So -16.4 you measure with the protractor. Then take your protractor and mark it on the P3. It face the protractor upwards as we need to mark the angle +16.4. So plus 16.4 means anti-clockwise, -16.4 means clockwise. So according to the thing, what I had told, it is the protractor is kept. And you just mark +16.4, -16.4, and you mark simply a dotted lines. No need to mark any other thing. Just mark simply the angles there, right? Then the poles, then let us draw the final branch. So the branch will start at P2, take angle -16.4, then it will meet the J 4.4 at the gain value K is equal to 8.8. Then when K is increased further, the branch will move to the right of S plane. It will travel, then it will take plus 90 degree, that is it follow the asymptote shape, and it will go to infinity in search of zeros. So this is branch number 2, right? So let us draw the branch number 3. So to draw the branch number 3, the same procedure. The pole will start at P3 by following the departure angle plus 16.4. Then it will move. Then it will meet -4.4. Then it will travel. Then approach the shape of asymptotes in search of 0. So this is branch number 3. So totally 3 branch. One branch will end at 0. Remaining 2 branch will approach infinity in search of zeros. It is P minus Z branch will approach infinity in search of zeros. What is the conclusion we can say about the stability from this given problem? So when K is equal to 8.8, when K is equal to 8.8, the branch will meet the imaginary axis. That is, the branches will meet the imaginary axis when K is equal to 8.8. It means when K is less than 8.8, the branches are in the LHS of S plane and hence the system is stable. When K is equal to 8.8, the system is marginally stable. When K is greater than 8.8, the branches are entering to the RHS. As the branches are entering to RHS, the system is said to be an unstable system. So based on the value of K, we can adjust the system stability. That is the biggest advantage of root locus. From the graphical method, it is a graphical method, and easily from the plot itself, we can able to determine the stability of the system. As root locus is a symmetrical plot, what shape you got above the real axis, the same plot will be, you can draw on the below the real axis. That is a key point you need to observe. So if you have equal number of poles and zeros, the branches will not approach infinity and all the branches will end at 0. There are many examples based on that problem. So in this problem we have 3 poles, 1 real pole, two complex pole and one zero. So one pole will end at 0, remaining two poles as approach infinity. When k is greater than 8.8, the system will become unstable. Thank you.